Okay, let's begin. Now, we have talked about last lecture, energy release rate, right? So let's do a summary of what we have achieved so far, right? We've been following Griffith, the energy balance analysis of Griffith, which is very insightful, very remarkable, very useful, really. Because from there, we can derive a fracture criterion, really the first fracture criterion that we have derived in this class, and also there's the first one that appear in the history of fracture mechanics. And that is based on a fracture criterion based on energy release rate and fracture energy, right? So the fracture energy is the energy resisting fracture of the material. It's a material property. And the energy release rate, has the same unit of the fracture energy, and this is an energy release rate that is available to make a crack advance by unit area. Okay. Now this is a slightly different concept from what you may heard before in mechanics, right? Now, so remember the energy release rate and the fracture energy. The unit of it is energy per unit area. So it's joules per meter square, for example. And so when we say rate, it's not a rate with respect to time. It's with respect to an advancement of crack area. So it's still a rate, but not with respect to time. So when you say the energy release rate, just be careful, what comes to your mind. Now, so what I want to do today is two things. We'll first summarize the fracture criterion that is based on energy, and see some of the applications, how we actually use them, how do we actually put them in design, because we have these concepts, we bypass the critical stress. However, we do need to have a way of calculating these things or measuring these things. So I'm going to summarize how we approach our first criterion and approach these things here. Okay, so this is what we have. Fracture criterion based on energy release rate. This is a process, right? So you can contrast that with the classical string theory, right? The classical string theory. Let's start from the bottom, right? Because that's what we wrote before, what we wrote last lecture, right? We have the G, which is the energy release rate. Our fracture criterion states that we must make sure that whatever energy that is available in the material, whatever that comes from, what we apply to the material, right? The loading applied, that must be smaller than the fracture energy inside of the material, right? So there's a material parameter that we can compare to. Now that is different from classical strength theory, which you compare the critical stress with the strength of the material. And now we understand there are quite a few things, deficiencies in that approach, and this bypass it, because to get to G, what do we need, right? We actually need to know the existing flaw size, the crack size, A. We need to know, obviously, what is being applied, right? You can apply stress. Sometimes you apply a displacement, which then translates into some forces or stress. Now, but then you can calculate that, if, with, for example, finite element analysis or so on. And that gives you an expression for the energy release rate, right? So I show you two examples, right? One with the Griffith, simple crack problem. And we derived an analytical solution. I also show you double cantilever beam towards the end of last lecture. So some of these expressions for the energy release rate can be derived analytically, but not too many, right? Really, not too many. If you know solid mechanics well enough, you find that a lot of things cannot be calculated by hand. It's very difficult to find closed form solutions. Now, then you take the fracture energy. Now that is a material property. Then you have to go to measure the material. Okay, this is something that most of the time obtained from experiments. So just like what you did with a fracture test, you go there and then you pull the material apart and then you note down what is the critical stress and that is not a material parameter, but that is done by experiment. So same idea we follow here, and then you measure that. So now let's think about how we apply this, right? So we actually have how many parameters that we need to know, right? First of all, we need to know the crack size A, right? There's always some pre-existing crack or flaws inside the material. This is a parameter we need, right, to be able to apply this criterion. So A is something we need. The stress is the other thing we need, right? Is the loading applied. The fracture energy, gamma, that is about the material. That's what we need. And also we obviously need G, right? So, but then G, once we we have these two, then we can calculate, right? There are, kind of four things around evolving this. And so, we can really apply, some of the, these, criterion in design. Now, but then first of all, we need to think about what are the, ways of obtaining these things. So first, start with energy release rate. Now, we know that the energy release rate is actually involves solving a boundary value problem, right? It's an elastic body with a pre-existing crack. We just need to find the elasticity solution to it. For Griffith and for English, they found the solution to the elliptical flaw. And you also, in your homework, are finding out the same problems with finite element analysis. So really, these are the two main ways of finding the energy release rate. Okay. So you either solve the finite, elasticity solution. You can solve it analytically. Some of them, very limited. Majority we do finite element. Obviously, a lot of these problems, or different crack geometries, have been solved analytically. Have been solved numerically, and they are documented in textbooks and handbooks. So one of them is here. The Stress Analysis of Cracks Handbook. This is one of the references in the course, and I also recommend you, take a read of that. You don't have to buy it. We are not going to use that, but then it's a very good reference. And a lot of that results have been documented there, right? So there are energy release rate, how you calculate them depending on the geometry of the material. Geometry of the solid, the crack length, what is the dimensions of the crack length, the dimensions of the solid, so on. So you can do that. Most of the time we do finite element today, right? So that's because they become very easy. Now the second way of finding the energy release rate, we actually talked about it last time, is that instead of solving the elasticity problem, you can measure compliance experimentally and use that to infer the energy release rate, right? So this is the second way, and I also described that method to you because this is what we got from last time, right? We know that in general, no matter this is load controlled or displacement control, if we know the compliance of the material defined as displacement over load, right? It's just the inverse of the stiffness. And we just need to know that, what is the compliance change with respect to crack area. And then we can calculate energy release rate, right? So I show you, if you can calculate compliance analytically, that's great. Then you can use this formula and apply it. That's actually this first approach. You solve the elasticity solution, you calculate. But sometimes you don't, right? Because the crack can be, your geometry can be very complex. So back in the days, this is a very common technique. No, it's still occasionally used today. So you can do that by just measuring directly the compliance. So I'll show you the thought process for this, right? So I think about we are trying to get energy release rate through the compliance, because compliance is something we can measure experimentally, right? Without having a way of calculating it, we can always just measure it. Now I'll just repeat the formula here. Now, so this is also brilliant, in the time where we don't have finite element method, right? And you have no ways of calculating analytically what is the solution. Then you have to, but you still got to live, right? You still got to design things, and you still need to use this. So this is experimental method, and it's brilliant, right? So you come up with a solution to a problem that can't be solved. So if we are back in the days, how do we tackle this? How do we measure G from through the compliance, right? So the idea is that, well, let's say this is the crack body, and I have some sort of crack, pre-crack A1. This is a thin plate, some width that I define, I know. This is quite a difficult problem to solve analytically, and we don't actually have a good analytical solution for this. So what you do is that you want to find the compliance, because you want to find the derivative of the compliance with respect to the area. So you just need to find the compliance of all these different crack bodies with varying length again, right? So let's say you make another A2 and yet another one. They all have same crack geometry, just increasing in the crack length, right? A3 is bigger than A2, is bigger than A1, all right? So let me... So next thing is that you want to find a compliance, right? So you take a load, you start loading it. You start with 0 and then a small load and so on. And then you measure, right, corresponding to a particular force P. Now you measure the displacement. You do the same thing. Okay. So again, that from what we discussed last time, we're going to see different force displacement curves from all these three, because they all have different stiffness because of the crack length difference. So what you need to do is that you want to plot the P delta curve for all these three cases. Okay, so they're going to be three different. They're going to look like this, right? So let's say this is linear elastic, right? So they can be, more than that. They can be more complex than this. They can be nonlinear, but general trend is that the most stiff one would be the one that is with the smallest crack, so as A1, A2, A3. They can be nonlinear, but anyways, they have to be more compliant in A3. So you can find the compliance of these three different crack bodies, because the slope of this is exactly the reciprocal of the compliance, right? So this is C1 compliance, C2, C3. So experimentally, once you get plot these curves, you find the slope of it, then you calculate, then you have a calculation of the compliance, right? So that's not the end, because we want the compliance as a function of area so that we can actually differentiate. So what you do is you take all these C values, which is the compliance values, and then you go to plot another data, which is C over A. Okay? That's the correct area. So area is just, in this case, A multiplied by B, which is the width. Now you have three different crack length, A1, A2, A3. So you're going to get three different points. Now, let's say that from these three, then you transfer over here C1, corresponding to the first crack. Then you plot it, C2. So C1 is going to, C1 is going to have the, the lowest compliance, right? and that corresponds to a smaller crack area, and that is what we expect. So what you're going to see is that a curve something like this, right? So compliance, it's less compliant means it's stiffer, right? Smaller crack, stiffer, less compliant. Larger crack, more compliant, and so on. So this you have, these 3 points, and you can make more, right? You can always obviously do more experiments by making more copies, and then you have a more precise curve from here. So now you can draw these points up, right? So they don't have to be linear. I'm just using this simple example here, and then you can calculate this from the experimental data, right? All these are experimental data. We have not written a single equation here, right? Other than all the definitions of compliance and crack length. Now, you can numerically differentiate, so you get a slope of DCDA. Now, if they are nonlinear, so they're not linearly changing, then your DCDA is not a constant. It varies with A. But then you can do that if you have more data points, you make more copies, then you get more precise calculation, and then you can calculate DCDA, which is just the slope of this, right? So then you go back to here, then you calculate the energy release rate, right? And this is completely experimental method, and we sometimes call this the compliance method. Now this, you see, obviously is quite time consuming, takes quite a bit of effort because you need to do the experiments, you need to make all these specimens and do careful experiments to be able to actually get this correctly. Now this is seldom used today just because we have finite element method, so pretty a lot more accurate than previous than before. So we can actually we don't use this so much these days, but this is the idea of doing that. Now let's go back to here. So we talk about how we calculate energy release rate. The next thing, obviously, we need is the fracture energy, right? So what are the ways of obtaining that fracture energy? Now, it's a material property, so the only way to do it, but there are 2 ways of doing it. The first one, again, is to measure it experimentally. So you follow the same sort of procedure that we described, and you apply the force, the stress onto the material, and then you can calculate the energy release rate, right? Because, for example, you just take the same geometry here, right? So we are doing a different thing now. We are not trying to get a compliance. We're trying to get the energy release rate at fracture. Okay, so what you need to do is, well, you keep pushing it until it breaks, right? That is the energy release rate right at breakage, right? So you just keep stretching it, and then suddenly it breaks. Now that is the energy release rate at fracture, right? So you just need to do one experiment, calculate that fracture as the energy release rate just when the P is the breaking force, and you can calculate that as a numerical value for the material, and that's fracture energy. So this is just the same sort of experiment, but you're looking at a different variation of the data, extract a different piece of information. Now, again, the fracture energy have been reported. Many people, many materials have been tested. We always do this because we always come up with new material. So we always, whenever we have new material, we do a fracture test. And materials can change. The same material can have different fracture energies if you change the conditions of treatment, and also if you change the composition slightly or the microstructure slightly, they can all change. So typically we always go to measure fracture energy, right? So in design, so we don't just rely on handbooks that from tests that people have done before, because you never know how accurate that is, and you never know if your material is exactly the same, even though you might be looking at concrete, and then you have another piece of concrete. They are nominally similar, but it's always in a range. Now here are some typical values, right, of energy release, fracture energy. So you have ceramics, that is a very low fracture energy material. It's brittle material. It doesn't take a lot to break it. So that's ceramics. It's 50 joules per meter square. Now you take polymers and steel; they're a lot more ductile. So a lot more energy goes into breaking it. There's plasticity that is involved, as we talked about before. So you see this, even though ceramics is very stiff, the fracture energy is not very high, right? It's actually smaller than polymers, right? So because these are two independent properties. Stiffness is stiffness. Fracture is fracture. They are not related. They are independent. So you can obviously, look on internet or in this literature, fracture mechanics literature, to look for the sort of fracture energy, right? So I measure it before as well, for ceramics. I also measure that for epoxies, for research. We do this quite often. So later on, I'll tell you how we actually measure these things. It's another area which is experimental fracture mechanics, which also become quite standardized. There are many tests that you can do. I'll show you some of the tests I've done before. Now the other way of getting it is this is fairly new. It's not really mature yet. Is to calculate that fracture energy by very high fidelity simulation of all the micro scale and nanoscale processes involved in the fracture process. Now this is extremely complex problem, right? So the idea is that you have breakage of a material. In the end of the day, that all the processes that went in. If you understand all the processes that are involved, then you can actually calculate the fracture energy, right? Without actually measuring it, right? So because plasticity, for example, for steel, there is if you understand the yield strength, the yield stress, how the dislocations happen, you can calculate, and then you can calculate how much area is being plastically deformed. You can calculate the energy dissipation. Now, then you go to the atomic scale, and then you calculate what is the energy involved by separating it, right? All these processes you can calculate. Obviously, they're not very mature because a lot of unknown in all these processes. So this is in research area, I'll say we don't do this because it hasn't had the fidelity. So we are not relying on this very much. So this is fracture energy. Okay, so there are some applications of it, right? So the way I talk, as we look at it, it seems like it's always just a few parameters that you are kind of playing around. But but if you think about this more deeply, in fact, this is quite insightful. You can use this to do a lot of things. So the fracture criterion, again, we write it here, is just G equals gamma, right? So when your G reaches gamma, you're going to break the material. So sometimes we know we know the crack size, we know fracture energy, and we don't know the stress, right? So there are different ways of using the formula, right? If you know the fracture energy of the material, and if you know the crack size, then you can go and predict what is the critical load, right? That's this one right here. So, right, because this criterion tells you that, well, if you know crack size, you go measure it, and then you take you do an independent test to measure the fracture energy. Okay, so I can now make a calculation of how much is the critical load that I should not exceed. So this is new information for design, because I now know that I should not load this material above certain stress. All right, so that's an application. So measuring a fracture energy, right? Sometimes you want to do a ranking or a comparison of different materials, right? So you're earlier in a design phase. So I want to find the right material for my application. So I know the loading conditions. This is a bridge, or this is a car. This is a ship. This is an aircraft. So I know approximately how much load is being applied, because I know for aircraft, for example, I have some pressurized inside the cabin. We have loading of the lift force and so on. Now I can then I pretty much know the stress being applied, right? So that's not what I'm looking for. But then I may have choices of alloy, and I have a choice of composite, right, to make airplane. So which one should I use? Obviously, I want to use composite because it's more lightweight, but is it going to have enough fracture energy, right? So you can go and measure alloy, and go measure composite. Okay, then you have two fracture energies, and then you compare them. Okay, maybe they are similar in fracture energy, so I'm good with composite because they deliver the same fracture energy, and it's lighter than alloy, than titanium, for example. So I want to use it, right? So this way you can compare materials and then use them for design. Now the third application is that you can estimate the floor size, right? Sometimes this is what you want to know, because this is something that you can also improve, and we do improve these things. For example, I was involved in making designing ceramics for solid oxide fuel cells, right? These are ceramic fuel cells, very brittle material, and again, the load case is pretty much known, right? Because we know how we want to use the solid oxide fuel cells. We know the processes that are involved. So the stress distribution is pretty much known. We can calculate it pretty accurately. And we know the fracture energy, right? Because we have this material, we tested them repeatedly in the lab. And so that's the fracture energy. So what I'm looking for is not a new material, because this is the material I want to use, because it has the the right combination of the chemistry and efficiency of being a battery and all that. So I don't want to change material, because I don't have another one to change to. So it must be this one. So then what I can do is that, okay, but it's going to fracture. Is it going to fracture? I don't know, right? Because that depends on the floor size. So I can go and see what is the floor size in the process of making this piece of material, and you can calculate based on this fracture criterion, and say that, well, the critical floor size, based on the stress being applied and the fracture energy of the material, is 5 microns. Okay. And so if anything that is beyond that, right, if my ceramic, the solid oxide fuel cells, have a crack size larger than that, then it's no good. So I have to, this becomes my design goal. I have to go to that manufacturing process and see, please make me this material, solid oxide fuel cell material that, has a floor size of smaller than 5 microns, right? So there are ways of doing that, right? So by, more careful processing. You can change the floor size. So this is, again, depending on what you can change and what you cannot change in your applications, this is quite useful, right? So because you don't always know everything. Most of the time you don't. And most of the time what you want to change is, or what you can change is quite limited, right? You may not be able to change material. Sometimes you may not be able to change the floor size because the manufacturing process it cannot be changed. And sometimes you cannot change the critical the load being applied, because that is the design criteria that it has to take certain load. So these are different aspects of the fracture criterion. So sometimes you can change things, and you can now divide the labor. Now the final point I want to make, as just to discuss, how we use this, proving structural integrity, right? So this is the case where you know everything, okay? You know the critical crack size, you know the flaw size in your material, and you know the stress being applied. You know the fracture energy. You know everything about it, right? And what you can do is that, I am going to take all this information and go use this fracture criterion and make sure that this is actually not failing. Okay, so this is actually a phase that we sometimes do for very critical devices. Okay, so if you think about ceramic tile, heat shield ceramic tile on space shuttle, they are ceramic tiles, right? Because they are insulators, and you have these ceramic tiles that put on the space shuttle, and they can't break, right? Because one of them break is quite disastrous. Actually, so we take every piece and load it before we put it on to the spacecraft, because you load it. Obviously, you make this calculation first, right? Because you examine the flaw size, using either X-ray or micrographs and all that, and you load it, and then you make sure that the fracture criterion is true, right, or it's not breaking at what I expect it to break, right? That's good, and then you individually just to go through all these ceramic tiles, right? Each of them to make sure, to prove that this is good to go. So from all of these, the one that is the most difficult to predict is the flaw size, right? So that's from my experience, and I think this is a consensus in the community of fracture mechanics, because first of all, some of these flaws can be so small, and you can't, it is difficult to spot them, especially if you have large structure. It's difficult to find them, and so it's a very time-consuming process. So this is how we apply them, right? So in design, so I just want to bring this up to you because so you can appreciate what we derived is not just a academic exercise, right? So these are the ways we use it. So just one more word on fracture energy. Now, fracture energy is a material property, but again is very dependent on conditions, external conditions as well, such as temperature and moisture. And all these things. So and we talked about that briefly as well. That sometimes you get a piece of steel, it can be ductile, but at low temperature it becomes brittle, and vice versa for ceramics. You heat it up, it becomes more ductile, and the fracture energy goes up. So these things is not constant, right? They have dependence on many factors. Experimental conditions and microstructures. It's a big field. A lot of research are trying to find out how this fracture energy depends on all these factors, and how do we improve them? How do we make materials? Because once you understand them, you can find a way to improve them. So this is fracture criterion based on energy release rate and fracture energy. Okay, so I want to start a new topic next, which is crack stability. Okay, so far we have the first section of the first section of the course. The screen. Is on energy release rate and fracture energy, and so that's pretty much done, right? So we want to use this to look at something more fundamental about the crack growth process, right? So that's we have the tools now to do that. So this is the topic that is also this is something we can use we can use the concept of energy release rate to predict, right? So crack stability, right? So what we did so far is to answer the first question, right? So if we have a crack, a pre-existing crack in a solid, is it going to grow, right? So far, by now we can answer that because we have a fracture criterion, and that exactly provides the answer to this, right? And so I can answer you, well, you go there and calculate the energy release rate, make sure that's smaller than the fracture energy. If so, it's not going to crack. The crack is not going to grow. Okay, that's the first question. Now we want to ask the second question from there. Okay, so now if it does start growing because the fracture criterion is met, what happens afterwards, right? So there's still some possibilities, right? Different possibilities. There are at least two. First one is that it's going to keep growing, right? The crack is going to keep extending, advancing until the whole body, fracture into two pieces, right? So that's scenario number one. And scenario number two is also possible. Is that it start growing at the beginning, right? Once G equals to gamma, that is, the condition is satisfied. Okay, it starts growing, but then after some time, after some advancement of the crack, it stops. Right, so that is a second possibility. Right, obviously a better possibility than the first one, because the first one means complete failure. So we call this problem the crack stability problem, right? So is the crack growth stable, right, or unstable? And we say that the crack growth is stable if the crack stops after some time, right? So both of them have, some crack advancement, right? So that's the first condition already met, right? They start cracking. We are asking this, what happens afterwards, right? So the stable crack growth says that, if the crack grows and suddenly, and after some amount of advancement, it stops. That's stable crack growth. Unstable crack growth is that the crack will keep growing. Now, so we want to determine, then what is the condition that determines whether we have stable or unstable crack growth. Now, so this is a different question, right? Because it's about how the crack is going to advance afterwards, and we do actually have all the tools we need to analyze this problem. So what we did, so I'm going to break down the whole thing, the whole concept of stability, just into three, fundamental concepts or essential ingredients in this. So we have something called the loading curve. I'm going to explain this in a moment. We have the resistance curve, and we have the initial crack length, right? So, to understand the stability, we need to understand these three things. So what is loading curve? So this is not a very commonly used term, but I like to use it because it differentiates from resistance curve. So I'll tell you why. So loading curve is related to the energy release rate, right? So think about the energy release rate and think about the fracture process. Energy release rate is always related to how we load the material, right? So we can change the energy release rate by how we change the loading, and it obviously also changes as the crack grows, right? The energy release rate can depend on the crack length. It also depends on how you load the material, right? The crack geometry and so This is whatever we've done to the material. Now, energy release rate can change with crack length, right? So, I mean, as the crack grows, that means that the crack length is increasing, right? So we want to see that whether the energy release rate is increasing, decreasing, or constant, right? Because if we know how it depends on that crack length, we know what is going to happen afterwards, right? So G, the energy release rate, if it increases with the crack length, then we have a worse situation than before, right? Because my initial G already reaches the critical fracture energy. And so the crack starts growing a little bit. And in that case, after the crack has grown for a little bit, the energy release rate increased even more. That means that there are more energy to make to keep the crack growing. So that is a worse situation, right? But if it decreases, the G decreases as the crack grows. That means that the situation is better. There's less energy to push the crack. Or a neutral situation where the G is staying the same. Okay, so it can vary with length, and it depends obviously on how the material is loaded. Anyways, so we can describe G as a function of A. It's not a constant, right? Because we actually know this. G can depend on crack length, and we call that the loading curve, right? The function of G with respect to A, we call it loading curve. Okay, not commonly used, so sometimes you talk about loading curve. Other people may not understand it. But I mean, if you talk about how energy release rate as a function of A, then we all understand it, because that requires no explanation. This is precisely defined. So let's look at Griffith crack. Just very simple example, right? We can see immediately this is a function of A, right? So this is something that we derived last lecture, right? Based on the Griffith crack, we based on the energy analysis of Griffith, we arrived at this expression, and it's obviously increasing with A, okay, and it's linearly increasing. So the energy release rate, the G function, the loading curve increases, so it's giving me a worse situation. But that's not the end of it, right? So just increasing G does not mean that the crack has to be unstable, okay? So it's not the only factor that determines stability. So let me talk about, before we go to the resistance curve, let me show you a different example that by changing the loading, we can change the G. Okay, so this is quite a good example to illustrate the concept, right? So we will look at double cantilever beam. Okay. So this is a case where we can analytically derive the energy release rate, which we did last lecture. All right, so I'm just going to redraw that. So this is the double cantilever beam configuration. We have applied load. We have delta, which is the crack opening. We have the, let's say, the cross-section. The height is h, width is b for the beam, right? This is the cross-section of the beam. So what we did, I'm just repeating what we have last time, right? From beam theory, we can calculate the compliance of the beam, and you can calculate the energy release rate in this situation, which is, P square, A square, B, E, I, right? So this is what we did last time. This is the energy release rate if you're loading the double cantilever beam by a force P, okay? So take a look at this. How does the loading curve look like, right? What is the GA function look like? It's increasing with the crack length because we have A square and G increases as A increases. Now it's even worse than Griffith crack because it increases with the square of the crack length, right? In Griffith crack, it's linear increase. Here is quadratic increase, so it increases even faster. So whenever the crack goes a little bit more, you get even more energy release rate available to advance the crack. So it's not so good. So this is G if you load it of the cantilever beam, if you load it by a force. All right, so there's another way of loading the cantilever beam, which is to put in a wedge. Okay? Instead of, pulling with two forces, you have a grip that I can control the force, I can hang a weight on these 2 points, then I can control the force P, and that is how I load the specimen. It's a load control experiment. The other configuration is I put a wedge. Instead of putting the two forces here and there, I just put a wedge in the mouth and I keep hammering this wedge towards the crack, and that is going to give me what? An opening of that crack, right? Because I'm trying to drive that wedge inside, and this is going to keep pushing these two slabs away from each other, and that will actually give a crack extension. Okay. However, the difference is that now I'm not controlling the force P. I'm essentially controlling delta, because I can adjust the wedge angle, and I can adjust how much I push this in. So exactly this much is delta, right? This is the wedge in this configuration, and right now this is the delta, the displacement of the crack at the mouth, right? So I am actually driving the delta instead of P, and this is a displacement control displacement control cantilever beam test. So in that case, what is the energy release rate, right? It's not the same here. It's not the same. Okay. So I'll show you how to calculate it. And in fact, this is not too difficult because look at this configuration. Look at this result, which is P square E square BEI, and you just go back and look at this. Now I don't want to express my G in terms of P because I don't know P. P is not something I control. I'm controlling delta now. I'm not controlling P. So let me go back here to the beam theory, right? That is still correct. Nothing changes. I'm just not controlling P now. I just return this, change this equation slightly to express P. I get 3EI delta over 2 A cubed, right? And I'll take a square of that. Right? The purpose of this derivation is I want to get rid of P squared, right? Because I don't have P. I don't know what P is. I can control delta. I want to instead express G in terms of delta. So I go back to this beam theory, and I got to find out, P squared equals to this. Now this is completely free of P. Its delta is in there because, and that's good because delta is what I have. Delta is what I control. I have crack length and the other parameters, and I need to just substitute here to get a new expression for G. And if you do that, you're going to get what? 9E squared I squared delta squared 4A to the power 6. That's P squared, and then I still have B squared BEI. Simplify that. 9 EI delta square 4 B A to the power 4. So let me circle these two different results. Right, so nothing has changed, right? It's still the same double cantilever beam, but I'm loading it a different way. I'm loading it with delta, right? And this gives, a completely opposite result because now G decreases with A. As A increases, which is the crack length, G reduces, right? So that's good. Think about this, right? The crack grows a little bit, actually G has smaller now, right? So there's less energy available by this loading method to advance the crack. So if the fracture energy is constant, that means that the fracture resistance does not change with A, then we will have a stable crack growth in this case, right? Because first of all, my G, which is as I'm loading this with the wedge, first of all, I'm going to start growing the crack once G equals gamma. Now gamma stays constant with A. Now A grows slightly. G reduces. That means now G is smaller than gamma, right? And so the crack stops because the fracture energy is no longer satisfied, right? So I'll formalize all that again in a minute, but just by looking at this result, we can get a lot of physical insights and then just explain this to you. What is the significance of these two, right? So, and take a look at also the dependence of A by G. This is square increase. This is called to the power 4. So it actually reduces very quickly with the crack size. So that's good. We like stable crack growth just because the crack growth is easier to observe, if we are doing experiments, and obviously if you're using it in reality, stable crack growth is good because it's not going to, lead you to complete failure, right? Obviously, we don't always have the choice to load material, right? So in applications, the loading is applied, by whatever is being designed for. But in experiments, we can choose how to load it, and we always choose the easier one to do, right? So this is, a smart way of doing experiments. So let's just draw this, or just sketch these plots real quick. So if we are talking about loading curve, which is the GA curve, so we are talking about the energy release rate as a function of the crack length. So look at Griffith. Griffith says, for the Griffith crack, the G is expressed by this, right? So it must be a linear curve. This is the loading curve for the Griffith configuration. And obviously it varies with sigma, right? So if you change sigma, you increase more force, you're going to get another, right? So let's say sigma 2 is larger, sigma 1 is here, but they're always linear with the crack length, right? So that's the Griffith loading curve. Now the double cantilever beam is different, right? Double cantilever beam, so the DCB loaded by a force. The G is DCB loaded by P, loaded by a force. P square, A square, BEI. Right, so if we're going to sketch this, again, this is going to be a quadratic curve. It goes like that, right? So you can see that different configurations, you get different loading curves, GA curves. And within the same DCB, you also get different loading, right? Because you can have DCB that is loaded by a wedge, and that gives you a different so this is DCB loaded by a wedge. Now you can see that now the G is going to be reducing. Now, so this is just the load, just to show you there are many variations of GA curve just by you changing the configurations, right? It's not the material. There's nothing to do with the material. Material is all the same here. So that is loading curve. Now I want to talk about the other part of crack stability, which has to do with the resistance curve. Okay. Let me go here. The resistance curve. Okay. Now resistance curve is the other part of the story, because resistance curve has to do with the material now. Now, so fracture energy, so it's related to the fracture energy. We know that the fracture energy is a measure of the fracture resistance. And many materials actually exhibit an increase in fracture energy when the crack length increases, right? If the crack extends, the fracture energy goes up. So not all of them have this behavior. Some of them stay flat, right? So the fracture energy is constant. Many brittle materials like glass, ceramics, they actually are pretty constant, right? And you seldom see any fracture energy that decreases with crack length, right? I can't recall anything I know that has less fracture energy with respect to the crack length extension, right? So if you increase in crack length, you reduce in fracture energy. Typically, I don't have that. I don't recall anything that behaves like that. So that's a good thing, because we typically see an increase or just constant, right? Constant, then we don't gain anything. But if we have an increase, that's good, because fracture energy increases. That means that we are more safer and safer as the crack lengths grow. And the function that express the fracture energy gamma as a function of crack length, known as the resistance curve. This is a very well, commonly used term now. So if you talk about resistance curve, or sometimes people will say that R curve behavior. Does your material show R curve behavior? That's what they mean, right? That means that is your material having a fracture energy that will increases with crack length? Right, so this is what we refer to resistance curve. So let me talk about the shape of that resistance curve. Right, let me draw this. Right, so we have two scenarios typically. Right, we have a scenario where we have a flat resistance curve. So we have the R curve. So two scenarios. First one that is a constant fracture energy. We have gamma here, crack length over here, and so we typically express that flat curve just like that. Okay. So this is the initial crack length. We have no idea what happens before, because we always start with a pre-existing crack in our material. Okay, so that is we don't know anything about material for smaller than the pre-crack length, because we measure fracture energy always with some pre-crack length, right? And this is an experimental value, right? This sort of is experimental finding, okay? So anything that you don't measure, you don't show it. So we don't know what happens here. But I know that if I start with some pre-existing crack, A0, and I measure it in experiment, I'm going to see that I have a fracture energy that is constant. If the fracture energy is constant, then it's just a flat curve. And the other way is a rising R curve. So really that is more the real resistance curve that we talk about. So typically what you see, these resistance curve plots is something like this, right? So you have an initial fracture energy. That is the first fracture energy that starts to grow the crack, right? That's the fracture energy. Once you reach that, the crack will start growing. Now, typically you have a rising R curve. It doesn't increase indefinitely. Most of the time it increases for a little bit, and then it again stays flat. Okay, or maybe very slightly increasing with a small slope. And so this is a rising R curve behavior. So if it reaches a flat, typically it does. Most of the material that we have seen behaves like that. It has a higher than the initial one, but it does stay flat. Okay. And we typically call this the steady state fracture energy. So SS, gamma SS, just to signify that, right? So there, typically we then characterize kind of rising R curve behavior of a material, saying that, well, what is gamma S, steady state fracture energy? What is the initial fracture energy? Okay, so then once we know these two, then we pretty much have characterized the material in terms of fracture resistance behavior. So I'm going to talk about why materials can have this behavior from a more micromechanical or micro scale perspective later on, not today, because it has to do with the material, and there are many ways. It's a very interesting area because if you can create our curve, that's a good thing. And actually, there's a big field. People do come up with different sort of approaches to induce or to impart rising R curve behavior in materials. So I'm going to talk about that a bit later, maybe a few lectures later, when I talk about the what happens at the micro scale and what is the mechanisms at the material level that determines the fracture process. And from there, then we can talk about why that we have this R curve behavior. So please just accept this for the moment, so we can go into talk about how we use this to write down a criterion for stability, right? Because now it becomes we have all the ingredients for us to actually draw some conclusions now. Stability of crack growth, right? So I'm almost done. Or stability criterion for crack growth. So what we need to do is just to put the resistance curve and the loading curve together on the same plot. Then we'll give it a lot of insights. Right, let's first of all consider a constant fracture energy material. Right, something like ceramics, brittle materials, they typically have that. They don't increase in fracture energy. Just repeating the plot here, right? So I also want to plot the energy release rate, right? So this is gamma. Okay, So energy release rate is G. They have the same unit, so I can put them on the same plot. And let's look at Griffith, right? So that's the Griffith. This is exactly what Griffith was dealing with, because he had a piece of glass that is, now we know it does not have an R-curve behavior. It's brittle. Only one fracture energy, does not increase. It's constant with respect to the crack length. And he has the Griffith crack configurations, which the energy release rate is given by this expression, which is linear. We just sketch that. So let me draw a few scenarios, right? Because there are a couple of different scenarios you can get. Right, so these are all possible loading curves, right? Corresponding to different sigma. Right? If I have sigma 1, small force, I start with a small stress, I'm getting this sigma 1. This is loading curve, right? And so what happens in this case? So that's the first question we need to ask. Is this going to crack, right? Will it satisfy the fracture criterion, right? Let's ask the first question first. Will it start cracking? Before we ask whether this crack will keep going or not, right? So think about this for a minute, right? So what does that mean? If I have a loading curve like this, that means the G. I have an initial crack, pre-crack length is A0, right? My loading curve is here. And obviously, this will not grow. Well, it doesn't satisfy the fracture criterion because what my initial, well, actually there's only one fracture energy is here, and at the pre-crack length at sigma 1, my G is here, is lower than gamma. Than gamma. So it's not going to crack at sigma 1. It's not going to grow. The pre-existing crack stays at A0. Now, what about sigma 2? Again, it will not, right? Because it's still under gamma. So I increase sigma 2. I keep increasing it. I keep loading the material. You are, actually moving this loading curve, rotating it clockwise, counterclockwise, as you are loading it, right? So what happens when it starts growing, right? So it starts right here, because now my loading curve is sigma 3. That is at this point, and it is the same. This is the critical condition. My G now equals to gamma, right here. So it's satisfied that fracture criterion is going to make the crack grow. Okay, now that's good. That's the first question. Will it start growing at that point at sigma 3? Now, the second question, will this crack keep going or not? Okay. So now, what we need to look at, it's the same curve, right? Because I'm applying sigma 3, and my gamma does not change. So what I have to look at is what happens afterwards, right? My G is going to keep increasing. My gamma stays the same. So that condition is being satisfied all the way. From here, once it's satisfied, initially it's being satisfied all along afterwards, right? So that means that the crack is going to keep growing. This is unstable crack growth. So that's why if you have a brittle material and you put it under a Griffith crack, once it starts cracking, it's going to zip and just completely, go through because of this behavior, right? The crack growth is not stable, right? So this is, the case with the unstable crack growth. Now we want to look at let's look at the other case, another case where we have a resistance curve, R-curve behavior. Yeah, actually, we're going to look at this next lecture because I'm out of time. So we're very close to the end, but so let's pick this up next lecture. I'm going to talk about, the resistance curve, and also we'll talk also about a cantilever beam to illustrate the different scenarios. So I'm going to see you next week. All right. Just one more thing about homework before I forget. So some of you have emailed me about homework, about the, whether you're on the right track. You're welcome to do that. I'm happy to give you comments. I just want to stress a few points. So when you do finite element analysis and you show your results, just be very careful to include all the necessary details so that I can understand what you're doing in your homework submission, because that is a very important part for any technical communication. You want to include the details that is necessary, but then don't include details that are not necessary. So don't dump, huge amount of, details and expect the reader to find it, because they won't and I won't. That's not my responsibility. The responsibility lies on the person who prepares the report, right? It has to be succinct, but detailed enough to reproduce, for another person to reproduce everything you did, and nothing more, right? And that's very important, and nothing more, okay? If anything more than that, and if it's not adding value, that is wasting time. So that's a negative thing. And so just, put that in mind, very basic things like units, what you're plotting, whether the shape, whether you're using scale factor, right? All these things, they all buried in finite element software, right? And you may be using them without knowing it. So I'm just stressing that because please, go through that. Think about whether what you're plotting makes sense. And if not, find out why. Because if you just show me plots without the understanding and interpretation, you don't get all the points. And because and that's very fair because everybody can use software now. The difference is whether you can interpret it. Okay, so yeah, that's all I would say. I'll see you next week.